Hey there everyone. Today's lesson is from chapter 11, section 1, and it focuses on solid geometry and cross sections. So in this chapter we're introducing three-dimensional figures, and so we start by looking at just solid geometry in general. So three-dimensional figures can be made up of curved or flat surfaces, but in this section specifically we're going to look at the shapes that have a flat surface. Each flat surface that's contained in a point is made up of what we call faces in geometry. So this figure right here, you can see that the face is labeled. The top of this box would be one face, the bottom would be a second face, and then you have obviously two sides left and right and two sides front and back. So in this figure, we have 6 different faces. Okay, you might think of them as the sides of a box. The edge is the segment that intersects the two faces. So the edge of our figure would be these segments that connect the two faces. So if you were to count all the edges in this figure, I would start from the top and count all the edges around my top face, so that would be 1, 2, 3, 4. Don't forget to count the edges along the side, 5, 6, 7, 8, and then the edges along the bottom of the figure, so that would be 9, 10, 11, and 12. So we have 12 edges. A vertex is a point that is the intersection of 3 or more faces. So in this figure, that would be the corners of our box. So that would be 1, 2, 3, 4, 5, 6, 7, 8 vertices. Okay. So just a little bit of an introduction with some vocabulary on how we refer to the different parts of our 3D shapes. Also part of our vocabulary are some very specific shapes. The first one that we'll talk about is a prism. A prism is formed by any two parallel and congruent polygonal faces. We call those faces bases in a prism. So you can have lots of different types of prisms. It is all dependent on the type of bases that you have. So in this picture, this is a triangular prism, but you could have a pentagonal prism, a hexagonal prism. The bases can be any of those shapes. Okay. A cylinder is like a special type of prism. It's not a prism because it is formed by circles. So the bases of a cylinder have to be circular. The definition of a prism is that they have to be polygons. So a circle is not a polygon. Pyramids are formed by having a polygon base, but instead of having a matching base at the top of the figure, they meet at a vertex. So pyramids you can think of as a type of prism that just doesn't have a top to it. It meets up at one point. And then a cone is similar to a cylinder in that it has a circular base. However, it, like the pyramid, meets up at a vertex. It doesn't have a matching base at the top. Okay. Here are some names for different types of shapes. A cube is a special type of prism. It has 6 square faces. Other prisms and pyramids would be named based off of the shape of their bases. So a cube is like a special exception to the naming rule. But for all of these, you can see that we name the prisms based off of their bases. So here, the bases are both triangles, so that's a triangular prism. Here, the bases are both rectangles, that's a rectangular prism. Pentagonal prism, and hexagonal prism. Likewise, we would name our pyramids the same way based off of the base that they have. So a triangular pyramid, a rectangular pyramid, pentagonal, hexagonal. Alright, so let's do a couple of practice problems where we first classify the figure, and then we'll name the vertices, edges, and bases. So in this first one, you can't see because it's a solid figure, but back here there's another vertex marked at A. So if that happens in a figure, and you want to be able to imagine what's going on behind it, all you need to do is connect that vertex to its adjacent vertices. So A would connect to D and connect to B, and A would also connect up to the vertex at E. So now we can see what we call hidden lines in our figure that really represent what's going on behind it. So if we look, what shape is our base? Our base has 4 sides to it, so that would be, we'll assume that it's rectangular. So this would be a rectangular pyramid. And then it wants us to name all the vertices, edges, and bases. So vertices would be the easiest. We have vertices E, D, C, B, and A, all of the points that are shown. Our edges are segments, and so we're going to list them as segments. We have the segments going around the base first, so segments AB, BC, CD, DA, and then the edges going up along the side of the figure as well, so BE, CE, DE, and AE. Okay, and make sure you write them with segment symbols above them. Lastly, the base. We only have one base in this figure, and our base would be quadrilateral ABCD. Okay. For letter B, they've shown you the hidden line of the circle that makes up the base of this this can, and so obviously most of us know that cans make up cylinders, so we would call this a cylinder. Cylinders have no vertices. They have no edges that meet, so there would be no vertices. There would be no edges, because there are no faces that meet. There are only two faces to this. We have circle P at the top and circle Q at the bottom. Those are our only two faces. Okay. The side of the can, we call that the lateral side, and that's not technically a face because it's curved. Okay. All right, so I'll give you a second to classify each of these on your own. Okay, so here are your answers. If you were to classify 1A, it's a cone, has one vertex at N. Its base is a circle. They didn't give us the center, so I just made one up. And then there are no edges to the cone. For 1B, this is called a triangular prism. The vertices, edges, and bases are listed. Only two bases, triangle WYX and triangle TUV. Okay, the other thing that we're going to talk about today are cross sections. Okay, a cross section is any time you intersect a three-dimensional figure with a plane, and the cross section is described as the shape that is formed by their intersection. So the hidden lines will help you see exactly what's being intercepted by the plane. If you look at letter A, this cross section only goes from this to this corner. It should match the base. So if you're not sure if there's a vertex back there, just look down at the base. The base is a triangle, so your cross section should match it. And you can copy that hidden line exactly up into the plane that you've written. So this cross section would be a triangle. For this cross section, you would copy the hidden line up. This is forming a circle. Our extension down here asks if you turn the orange planes into vertical planes, what would the resulting cross section be? Well, if we look at this one, if we were to slice going vertically here, we would still have a triangle, and I can show you that by drawing the hidden lines behind it. From the vertex up here, if I was to slice down the back side, down to the back base here, and then along the base of the triangle here, I would still form a triangle with my top. So for this one, when we slice down the pyramid, it's still going to form a triangle. But if you look at the cylinder over here, if you were to slice vertically here, we would go straight across the top, down the bottom, straight across the bottom, and then back along the back side of the can. And so what shape would that make? It'd be a rectangle. Okay, so be careful which direction you're cutting your cross sections, because you may get different shapes depending on the direction that you cut the figure. Try these two on your own. This cross section forms a hexagon. It's parallel with the bases, so it'll hold the same shape as the base. And this one is vertical, goes against the bases, and you can see that it would form a triangle. If you were to turn the planes horizontal, then this one would turn into a rectangle, and this one would turn into a circle, because now it's parallel with the base. Okay, our last thing that we're going to talk about is how to generate 3D figures using rotation. So when you imagine a rotation, you want to imagine it as if the figure is being reflected over to the other side, but also rotated into that position. So in 3D space, we're going to picture this triangle being rotated over to the other side of the line. So if it helps you to visualize it, you can go ahead and sketch where that would be when it reflects over the line. Okay. Should be symmetric. Just get as close as you can. Okay. And now, when you think of rotation, you need to remember that things are going to be round when they rotate. So this vertex is going to reach this other side in a circular path. So it's going to actually rotate out around in front of the pole and come to the side, and then rotate around behind the pole. Okay. If you fill in that rotation, you can see that if this is circular down here at the bottom, this 3D shape will look most like a cone. Okay. Let's try another one with a different shape. Try this rotation created by the rectangle. Okay, if you rotated, or I should say, if you reflect the rectangle over the axis, you would see what it's going to look like when it rotates to the other side. But remember, its pathway to get to the other side is circular in motion. So you want to connect these with a curve all the way to the other side and then all the way behind the pole. So we're working in three-dimensional space. If you were to rotate this around the pole, it would form a cylinder. All right, and for our last section, we're just going to talk about some different terminology for prisms. The altitude is a perpendicular segment that joins the bases. Okay, so the altitude could be the same as a side of your figure, but not necessarily. So the altitude for this prism is the exact same as its edge going along the side. Okay, if that occurs, if the height is perpendicular along the edge, that means it's called a right prism, because it forms a right angle with its altitude. However, if your height, when you draw it perpendicular to the base, is not along the edge, that means you have an oblique prism, which basically means that the prism has been slanted. I like to imagine oblique prisms as like deck of cards that have kind of been shifted to the side. They still have the same base on the top and bottom, just like a deck of cards would, but the height is the same, but it's just slightly off kilter. Lateral faces just mean the sides along the faces along the sides of the prism. Okay. If you notice in a right prism, all of the lateral faces form rectangles, but on the oblique prisms, the lateral faces have been slanted, and so they're non-rectangles. They're more like parallelograms. Okay. As far as pyramids go, we have a couple of other vocabulary words. The faces along the side, again, are called lateral faces for both pyramids and for prisms. The altitude for your pyramid, again, is the perpendicular height from the vertex down to the base. And we have our base edges around the base, and then we have our lateral edges around the sides. Okay. One thing that you may see is called the slant height. The slant height measures the height of a side instead of the height of the pyramid itself. So you may be given the slant height and asked to solve for the height itself. And I'll show you how to do that. So just to practice our vocabulary, go ahead and fill in all of the vocabulary, hit pause and fit in all the vocabulary we just talked about in reference to this figure here. Okay, and so if you filled in the vocabulary correctly, MTV forms a lateral face. MP is our altitude to the figure. WSVT is the base. Segments MS, MV, MW, and MT are all along the sides, and so those are our lateral edges. MR is called the slant height because it's the height of that face. And when we're trying to solve for the actual height using the slant height, we know that the slant height and the height form a right triangle. You can see that by connecting P and R here, and this is knowing that this is perpendicular to the base. Okay, that's it for today.